Hi, welcome to Making Measurements, Making Decisions, and Making Money, a taste of decision analysis. So most of the videos on this channel focus on the methods of science, mathematical tools, and how we draw conclusions from data and quantify our certainty of those conclusions. In this video, we'll look at applying knowledge we get from a measurement to make a decision. We'll look at a scenario from the world of business. We'll use a simplified scenario where you take a measurement to determine whether or not to launch a new product. We'll see how mathematical tools explained on this channel can be used in the decision-making process. In doing so, we'll be touching on the subject of decision analysis. Here, we'll only look at a fairly simple example, and we'll skip most of the mathematical details. Near the end, we'll discuss some of the oversimplifications that we have made. We'll also point to other videos where more information on the mathematical tools can be found. More complex scenarios with more math will be covered in other videos in the Decision Analysis playlist. Okay, let's get started. So let's outline our scenario. Let's say you work at a company that sells a popular product nationwide. The company is considering offering an upgrade to its current product, but it is not clear if enough people would take the upgrade to make the upgrade profitable for the company. If the upgrade loses money, it will not be catastrophic for the company. The upgrade is also not expected to be wildly profitable. So there is no strong opinion either way on whether or not offering the upgrade is a good idea. Management has decided on a very simple criterion to decide whether or not to offer the upgrade. Management has decided that if the upgrade has a probability greater than 50% to be profitable over the next 2 years, the company will offer the upgrade. If its probability of being profitable over the next 2 years is less than 50%, the company will not offer the upgrade. Management has given you a small budget and asked you to determine the probability that the upgrade will be profitable over 2 years. Now, the company's product requires a subscription. Almost all customers are returning customers, and normally the vast majority choose to renew. So the company is confident that their sales, which have been 12 million units per year, will be essentially unchanged in the near future. The company thus anticipates selling 24 million units of its product over the next 2 years. The upgrade would be offered to the customer at the time of sale or renewal. Now, the finance department has done a detailed study of the cost of the upgrade rollout. They say that the upgrade will be profitable over the next 2 years if over 1.2 million customers in that time can be convinced to take the upgrade. This means that 5%, that's 1.2 million divided by 24 million, of the customers would need to accept the upgrade for it to be profitable over 2 years. So you want to figure out if more than 5% of customers will take the upgrade. You decide to offer the upgrade in a limited test market, about 1% the size of your total nationwide market, for 1 month, the month of July. You check the number of renewals coming due in your test market in July. You conclude that the number of July sales in the test market will be very close to 12,000. So you want to know if at least 5% of sales will include the upgrade. As you will be looking at 12,000 sales in your test market in July, this would translate into 12,000 times 5%, that's 600 customers, accepting the upgrade. But even if more than 600 customers in your July test market take the upgrade, that does not necessarily mean that more than 5% of all customers over the 2 years will. To see this, let's imagine that the rate of customers in your whole market over 2 years accepting the upgrade was, in fact, 5%. In this case, out of a randomly chosen subset of 12,000 customers, 600 would take the upgrade on average. However, out of any given group of 12,000 customers, more or fewer than 600 might take the upgrade. The actual number is probabilistic. If we knew how many customers in the whole market over 2 years would accept the upgrade, we could calculate the probability of a certain number in the test market accepting the upgrade. Let's call the number in the test market who take the upgrade M. The probability for exactly M customers in the test market to accept the upgrade would be reasonably well described by a Gaussian distribution. As an aside, we should note that technically the probability for exactly M customers in the test market to accept the upgrade would be given by the hypergeometric distribution. The Gaussian distribution, however, is a good approximation in this case. It will give probabilities within a few % of the correct result. It's also much easier to use, so we'll employ it here. In this video, we won't go through the math to show that the probability for M customers in the test market to take the upgrade is approximately described by a Gaussian curve. But if you'd like to know why, you can find that information in other videos on this channel. We'll give pointers to those videos at the end. For the moment, let's imagine it was true that 5% of customers in the whole market would take the upgrade. Here we plot the resulting probability for M customers in the test market to take the upgrade. On average, 600 customers in the test sample take the upgrade, but the number can be less than or greater than 600. Let's call the average number of customers in the test market who take the upgrade the expected number to take the upgrade. So if 5% of customers in the whole market take the upgrade, the expected number in the test market to take the upgrade is 600. So that's 5% of 12,000. The observed number who take the upgrade in your test market, M, can be larger or smaller than the expected number. Let's compare this to two other cases. First, the case where 4% of all customers, that's nationwide over 2 years, would accept the upgrade. And second, the case where 6% of all customers, that's nationwide over the 2 years, would accept the upgrade. In the first case, the expected number of customers in the test market taking the upgrade is 480. That's 4% times 12,000 people in the test market. In the second case, the expected number is 720. So that's 6% times 12,000. Here we plot the probability for M customers in the test market to take the upgrade for each case. As before, the blue curve is for the case where 5% of all customers take the upgrade. So the expected number in the test sample is 600. The green curve is for the case where 4% of all customers would take the upgrade, so where there are 480 expected in the test market. The case where 6% of all customers would take the upgrade is shown in red, so that's when there are 720 expected in the test market. In all cases, M is most likely to end up near the expected value. If 4% of all customers would take the upgrade, M will probably be around 480. And if 6% of all customers would take the upgrade, M will likely end up near 720. Note that, for example, in the case where 4% of all customers would take the upgrade, it is still possible that M will be around 700. However, while not impossible, events like this are very unlikely. So, you want to know the probability that the true rate of customers accepting the upgrade is more than 5%. This is the same as figuring out the probability that the expected number of customers out of 12,000 accepting the upgrade is more than 600. So your goal is to figure this out from M, the observed number of customers out of your sample of 12,000 accepting the upgrade. We've seen that if we know the expected number of people in the test market accepting the upgrade, we can write down the probability for M customers to actually take the upgrade. It is well approximated by a Gaussian distribution centered on the expected number, which is the fraction of people taking the upgrade in the whole market times 12,000 customers in the test market. But what we want to know is the reverse. We want to measure M, the number of people in the test market who take the upgrade, and from that get the probability for the expected number to take the upgrade. In order to do this, we need to use something called Bayes' theorem. Now, Bayes' theorem is the perhaps mysterious-looking equation that's read as the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. We won't go into detail about where Bayes' theorem comes from or how it's derived here, except for one point. Often, if we assume some hypothesis is true, it is straightforward to calculate the probability that a certain outcome will result. For example, let's flip a coin 4 times. We can calculate that if it is a fair coin, its probability of coming up heads twice and tails twice is 3/8. But what we often actually want to know is, given that the outcome occurred, what is the probability that the hypothesis is true? This is often much less straightforward. For example, if we flip a coin 4 times and it comes up heads twice and tails twice, what is the probability that it is a fair coin? That is a much harder question. However, Bayes' theorem lets us relate these two types of questions to each other. We can relate the probability that we want to calculate, but which is hard to get, to a probability which is easier to calculate. In our example here, if we know the expected number of customers in the test market who will take the upgrade, it is fairly straightforward to calculate the probability of M customers in the test market actually accepting the upgrade. But what we want is, given that M customers in the test market take the upgrade, what is the probability that the expected number is a certain value? Now, we won't go through the full machinery of using Bayes' theorem in this video. Instead, we'll just give results to give a flavor of what kind of results can be obtained. There are many videos on this channel which focus on Bayes' theorem, including some that go through calculations similar to those here in detail. We'll list those videos at the end. So you're going to go through with the test launch of the upgrade and see how many customers M in your test market decide to accept it. Then, given that value of M, you want to get the probability that more than 5% of all customers would take the upgrade. This is equivalent to asking for the probability, given that M customers in the test market are observed to actually take the upgrade, that the expected number of customers in the test market taking the upgrade is greater than 600. Let's call the expected number of customers accepting the upgrade in the test market lambda. So we want to know the probability that lambda is greater than 600 given the observed value of M. We write this as P of lambda greater than 600 given M. We'll use Bayes' theorem to get the answer to this. However, Bayes' theorem needs more than just the result of the measurement to give you an answer. To use Bayes' theorem, you must make some initial assumptions about the probabilities of your hypotheses before you make your measurement, or equivalently after your measurement, but not taking the result of the measurement into account. These assumptions are called priors. In case you'd like to touch base with the equations, this means that we have to make some assumption about the quantity in Bayes' theorem, P of A. In our example here, this means that you have to make some assumptions about the probabilities for lambda to fall in certain ranges. So you think about what you consider reasonable values for lambda. There are 12,000 customers in your test market, so lambda can be anywhere between 0 and 12,000. You decide that you have no idea what lambda is and take all values between 0 and 12,000 as equally likely. This is the assumption, or the prior, that you'll use in Bayes' theorem. Okay, so you go through with the test launch. In your test market, in the month of July, a total of 650 customers took the upgrade. So M is equal to 650. Let's look at what Bayes' theorem, plus our above assumptions, tells us about the expected number of customers in the test market accepting the upgrade, lambda. Given our assumptions and approximations, the probability distribution for the expected number, lambda, given by Bayes' theorem, can be approximated by a Gaussian centered at lambda equals 650 and with a standard deviation, which is a measure of the width of the distribution, sigma, approximately equal to 25. We show this distribution in the plot at right. Note the change in the horizontal scale from previous plots. The height of the curve gives the probability for lambda to fall between two successive integer values. For example, the probability for lambda to be between 650 and 651 is approximately equal to 0.016, while the probability for lambda to be between 680 and 681 is approximately equal to 0.007. Now, to figure out the probability that lambda is greater than 600, we add up all of the probabilities for bins of lambda above 600. This corresponds to the purple shaded area. Now, the peak of the curve is at lambda equals 650. The standard deviation sigma of the Gaussian is approximately 25. So we want to know the area under the curve between lambda equals 650 minus 2 sigma and lambda equals infinity. Luckily, this is easy. Let's say one wants to know the area under some region of a Gaussian curve. We can measure the positions of the lower and upper edges of this region in terms of the number of sigma they are from the peak of the curve. Then we can look up in a table to find the area of the band under the Gaussian curve. In the video Features of the Gaussian or Normal Distribution Part 2, Probability Bands and the 68, 95, 99.7 rule, we give some rules of thumb that can come in handy for evaluating areas under Gaussian curves. There we saw that the area under a Gaussian curve in a band covering 2 sigma on each side of the peak covers 95.4% of the total area under the curve. Here we show this area in red for a Gaussian centered at x equals 0 and with sigma equal to 1. This leaves 4.6% of the area outside of the red band. 2.3% is in the upper white area, and 2.3% is in the white area on the lower side. This will help us solve our problem here. The peak of the curve is at lambda equals 650, and sigma is approximately equal to 25. We want the area under the curve for values of lambda greater than 600, and 600 is about 2 sigma below the peak. We just saw in the red and white plot that the white area under the curve is approximately 2.3% of the total area under the curve. This means that the purple area is about 97.7% of the area under the curve. So we estimate that the probability that lambda is greater than 600 is 97.7%. This is the probability that at least 5% of customers in the whole market will take the upgrade. So you have your result to report back to management. You estimate the probability that more than 5% of all customers will accept the upgrade as 97.7%. Based on this, management will decide to go through with the full launch. Now that we have that result, let's discuss it. Okay, first let's make a minor point about approximations. Here we've taken the probability distributions for m and lambda as Gaussian. They won't be exactly Gaussian, so this will introduce an error in our probability estimates. Here we concluded that the probability of a profit was much greater than 50%, so these errors won't change the conclusions. But in trickier cases, more care might be needed. Also, in this example, we took the test market as being perfectly representative of the market as a whole. Realistically, the test market won't behave exactly like the whole market. For example, the test market may, on average, contain people with higher or lower incomes than the whole market. Additionally, people's willingness to accept the upgrade may change with time as word spreads and more people learn about it. In a more realistic example, we would wish to take into account these possible systematic effects by assigning an additional uncertainty to the expected rate of people accepting the upgrade. Okay, next, let's talk about that assumption that was made in order to use Bayes' theorem. Bayes' theorem required that we make upfront assumptions about the probabilities for lambda to fall in certain ranges of values. Here we took all possible values of lambda between 0, which corresponded to nobody in the test market taking the upgrade, and 12,000, which corresponded to 100% of people in the test market taking the upgrade, as equally likely. So the result that we got depends on this assumption. What if we had made other assumptions? For example, perhaps a colleague who has been at the company a long time says that they've launched many upgrades to products in the past, and they've never had more than 20% of customers accept an upgrade. They tell you that it's most common for 1 to 3% of customers to take an upgrade, but it's not rare for as many as 10% to accept it. So you think that maybe you shouldn't have taken all values of lambda between 0 and 12,000 as equally likely. Maybe instead you should have assumed low values of lambda more likely and large values less likely. If you had done this, you would have obtained a different result. Specifically, you would have obtained a smaller probability that at least 5% of customers would accept the upgrade. However, while your priors are important and do affect the result you'll report to management, in this case they probably wouldn't change your conclusions all that much. Roughly speaking, which priors you use will matter less if the uncertainties on your observation are small. Here, you had fairly good statistics from which to base your conclusions. You had 650 customers accepting the upgrade. If you had used a much smaller test market, however, your starting assumptions could be much more important. For example, if instead of 12,000 people in your test market, you had only 1,200 people, and only 65 of them, instead of 650, took the upgrade, your choice to either use a flat initial prior for lambda, or follow your colleague's advice to favor lower values of lambda, would have a much larger effect on your final conclusion. So roughly speaking, the prior you use matters, but it will be less important if you get better data. Next, we've tried here to give a very simple example of how to use tools from physics and statistics to make decisions. But our scenario here has been perhaps too simple. Let's discuss a few ways in which our example could have been more realistic, although admittedly more complicated. First, we took as given that the finance department knew the costs of the upgrade with high certainty and had concluded that 1.2 million sales of the upgrade would make it profitable. However, in realistic scenarios, the information on the costs themselves may be estimates with uncertainties. So one would have to take into account different possibilities for the cost of the project to figure out the probability of making a profit. Second, here we dealt with making a decision based solely on whether or not a profit is likely. This was not too crazy, as the losses or gains from the upgrade were expected to be similar and not expected to be large. But in most scenarios, one would probably want a more complicated criterion. For example, if prospective gains were likely to be much smaller than prospective losses, you would want the probability of a gain to be much more than 50%. Conversely, if prospective gains were likely to be much larger than prospective losses, you may be comfortable with having the probability of a profit be less than 50%. Additionally, one might have a situation where there are multiple different avenues available, each with its own estimated revenues and costs and their uncertainties. For example, the company may be choosing between launching this upgrade and launching another product. So instead of just trying to make a profit, instead you might want to make a decision to maximize profit. On the other hand, one could imagine a situation in which the financial shape of the company is not great. In such a case, while profit is desirable, it may be more important to prevent a loss. So you might be willing to give up opportunities for large gains in order to minimize the probability of a loss. You may wish to minimize risk. We'll explore some scenarios along these lines in other videos in the Decision Analysis playlist. We'll also go through the math a bit more rigorously in those other videos. Okay, so in this video we've tried to outline how some of the tools from physics and statistics can be used in decision making. We've left out a lot of details, but many of these can be found in other videos on this channel. Here we'll point to some of those videos. Links to these videos can be found in the description below. In this video, we made use of the hypergeometric distribution and approximated it as a Gaussian or normal distribution. More info on the hypergeometric distribution can be found in the hypergeometric distribution playlist. For more about the Gaussian distribution, you can check out the Gaussian statistics playlist. To understand how we obtained areas under Gaussian curves, you may want to watch the aforementioned video, Features of the Gaussian or Normal Distribution, Part 2, Probability Bands and the 68-95-99.7 rule. To understand how and when the hypergeometric distribution can be approximated by a Gaussian, you may also want to look at the videos in the Binomial Statistics playlist and Poisson Statistics playlist. Another important topic in this video is Bayes' theorem. For an introduction, you may be interested in the videos in the Bayesian playlist. In particular, an example similar to what we've done here is worked out with all of the mathematical detail in the 4-video series entitled Why Bayes' Theorem is Important. And finally, more examples of using the tools of science to make decisions will be explored in videos in the Decision Analysis playlist. Okay, let's summarize. Here we've tried to give a simplified example of how using the tools of science and statistics can help in decision making. In particular, this example utilized features of the Gaussian distribution and Bayes' theorem. More details on these tools can be found throughout this channel.